Welcome to Class 3 of Introduction to Digital Color Theory. You've already heard about black, we're calling that code 0, and white, we're calling that code 1. You've already heard about how white in acquisition can be at various levels of luminance, and normally at capture time we set iris, set exposure, set gain, such that in the bulk of the image processing chain, white is considered to be 1.0. Now, we'll have some discussion later on in the class about the desirability for some headroom above diffuse white. And the cinematographer and the color grading person, the colorist, are free to depress the level of diffuse white shirt or paper white below the reference level of white if that meets their aesthetic objectives. But more on that later. The topic for today is called perceptual uniformity. And you won't find this topic discussed very much in color technology courses. And some people might think that Poynton is kind of crazy to be spending so much time talking about this. But I believe it's hugely important to understand not only black, we're calling it 0, white, we're calling it 1, but the behavior of light power, light intensity, linear light values as a function between those two reference points. And more particularly, how the physical linear light photon power energy scale, which is appropriate for VFX and CGI, relates to a more perceptually optimized scale, which is appropriate for mastering and distribution and display. And the latter part of that, the mastering, distribution, display standards, I'll put quotes around them because some of them aren't very well standardized, but they historically have all been based on a perceptual representation, not a physical representation. And I use two hinge points to talk about that difference. One of my hinge points is 18% gray. And so to pick my DSC Labs Cameline chart, actually this is called CAMET, the background to this chart has a reflectance of 18%. So in VFX CGI space, you'll want that to be coded as the number 0.18 on a scale of 0 to 1. In other words, an OpenEXR value of that reflectance will be ideally 0.18. However, in the back end of all of our imaging systems on the way into the distribution channel and for display, that 0.18 is mid-gray perceptually. And so in commercial imaging systems, we boost that up to halfway up the scale. And if I can show you one example of that, I've constructed this example, and I constructed it a long time ago with Photoshop version 5. The window borders and the decorations have changed, but the principle is still exactly the same. If I make a gray disk, or even if I capture that as a gray level from 18% gray in the scene, like the background of this chart, bring it into Photoshop with relatively default settings, and look at the pixel inspector, I get values 128, 128, 128, halfway up the Photoshop scale 0 to 255. So Photoshop is reflecting a perceptual coding of that gray value suitable for the back end, and it is absolutely not 0.18 of the way from 0 to 255. So let's talk more about this concept of perceptual coding, and I'll give you my other kind of hinge point for this discussion is what I call code 100. And that refers to what the gray level would be if you had a Photoshop picker 100, 100, 100, using integer 8-bit numbers 100 on the scale from 0 to 255. Now, in this whole discussion, I'm going to pretend that it's feasible to have such code values, a 0 to 255 scale, in the linear light domain. So where an 18% gray would be coded as 0.18, of the way from 0 to 255. But I'm going to use code 100 as my hinge point for a reason that will become clear in just a moment. I'd like you to think of this test card that you would place in front of a human observer to do an experiment. So it would be a card that would be very roughly comparable to this, but simplified, comprising only a disk on a background. And the Camet background is 18%. Doesn't really matter what the background is here. What's important is we have a gray patch with luminance L and a gray patch with a slightly higher luminance L plus delta L. And the experiment that you run on the human observers is you try to figure out how small can I make that delta L so that those two disks are visually the same. Even though you might be able to use an extremely accurate measuring instrument to measure a difference, the key question is, can I see the difference? Because as soon as I drive that little delta L to a small enough value that I can't see the difference between those two halves, then I don't need to represent that data with any additional precision as far as the requirements of human vision are concerned. So we've reached the point where we determine the step from one pixel value to the next pixel value that's just on the verge where it won't be noticed. And that's exactly the same place where you could think of taking delta L and starting at 0 and making it bigger and bigger and bigger until I just do notice. And whether you notice or not is really a statistical question. It can only be averaged across a number of observers or a number of experiments. There's no absolute hard line. We're just trying to get a general notion of where you can see the difference and where you can't. So you could call this the just noticeable difference, the JND. Now, this experiment, I'm producing measurement values L plus delta L in linear light space, so directly proportional to the photon count or the optical energy in front of the camera. So this would be in a domain that I'm calling the linear light domain, very familiar and comfortable to VFX and CGI guys. This is the basis for the ACES color space that's in development for digital cinema acquisition. So in my experiment, I'm assuming that we've got linear light coded in 8 bits with reference black 0, reference white 255. And the question is, what happens around code 100? Now, if you run that experiment, L plus delta L, what you conclude is that the human viewer can never see those two patches as being different. In other words, we always see them as indistinguishable whenever delta L is less than about 1% of L. So the distinction doesn't go by an absolute photon count. It's not an absolute number. Rather, it's a ratio depending on L. And the ratio just at the verge of perception is around 1% of L. Now, what that means is that code 100 occupies a special place, because that's the place in the linear light code scale where going up to the next code is a jump of exactly 1%. And the problem with linear light coding, and what I call the code 100 problem, it's really two problems. One problem is what happens below that level of luminance. Another is what happens above that. So let's first go to what happens below. At around code 20, the ratio to the next available code level 21 is 5%. That's way above our 1% rule of thumb number, and we think that we're at risk of having a visible step introduced whenever we make that jump. Now, you may think of this in visual terms as a beach ball. Let's make it a gray beach ball sitting on the beach at Santa Monica, bright sunlight coming down from the sky, but there's shadows underneath. And if the beach ball were at code level 50, but then we go to code level 40, code level 30, code level 20 as it gets darker and darker, and way down at the bottom of the beach ball we go from code 22 to 21 to 2019, the trouble with this 8-bit linear light coding is you'll see scallops underneath the beach ball where we go those jumps, 22, 21, 2019. And those scallops or banding or contouring artifacts aren't there when you look at the beach ball when you're actually on the beach. So the problem is that the coding system, 8-bit linear light, has introduced that banding problem below code 100. And that's a serious problem. It's a big deal. Now, there's not only a problem down below code 100, there's a problem above code 100. And I'll exemplify that by code 200, where if you imagine the shift to the next higher level, 201, the ratio between those is 0.5%. Nobody can see it. You might as well go directly to code 202. So above code 100, the code levels start becoming wasteful for human perceptual purposes. Now, one way around this whole problem is push that code 100 to such a low level of dark gray that we don't see those banding artifacts anymore. And you can do that by choosing a scale way higher than 255 to be the top end of your scale. Here I use the example of 4095, again in the linear light space, but now a 12-bit number. And this linear light 12-bit coding is absolutely typical of, let's call it midstream or mid-tier digital cinema cameras. This was Red 1. This is ARRI D20, D21. This is Sony F900. They all use 12-bit converters. So they all had code 100 problems of bandering and contouring in the really, really dark shades. But going to 12 bits instead of 8 has pushed those problems to such a low level of gray, roughly contrast ratio of 40:1, that you tend not to be able to see it. However, now we've introduced a very serious problem in terms of the efficiency of that coding, that if you think of the jump from 4000 to 4001, the next available code, that's only 0.40%. And that is so low, nobody would ever in a zillion years be able to see it. In fact, the human observer will not be able to see 4002, 4003, 4004, 4005, 4006. Those codes are all perceptually useless until you get about code 4040, which is now up 1% from code 4000. So those 39 codes in the middle are useless perceptually. So now you've already got an introduction to a little bit about bit depth. So 12 bits is fine for human visual perceptual purposes. We've pushed the code 100 problem so low on the scale that we're not likely to be able to see those artifacts, but it's not very efficient. And you can get away with 8-bit coding provided that you distribute the codes differently along the scale to overcome this issue that there are not enough codes in the deep areas of black in linear light, and there's too many in the highlights in linear light. So we code into a nonlinear physical form, and I'm calling it perceptual. And we do so with one of two kinds of mathematical functions, either a power function, which I introduced the other day as one example being CIE L star, and that's Photoshop Lab Space. But honestly, more commonly, the power functions we used are associated with gamma in a video camera and in a video display. So basically, historically, a video camera would use something like a 0.42 or a 0.5 power function, very, very roughly comparable to a square root, to come into a perceptually coded domain, and then the display would go out of that using the inverse, roughly the inverse of that power function. And just recently in 2011 or 12, HD gamma display was for display was finally standardized at the value 2.4. The other way to overcome this bit depth issue, the fact that to record linear light requires a lot of bits, the other way is to use logarithmic coding. And that's now fairly common for acquisition, and there's many different log forms. However, nobody has standardized an anti-log at the display. So even though a log format is a perfectly reasonable way to come into DI or post-production or grading, you'll want to do some transformation from log code because all of the distribution formats are based on gamma or power function coding. And I'll give you a few of those different standards in a few moments. But log coding, perfectly reasonable for acquisition, but not yet standardized or practical on the way out. Now, I've been assuming throughout here that there's some function coming in from a large number of codes, say in a camera, and quantizing to a fixed number of steps. Now here I've only drawn 11 steps, but you already know that we'll need at least maybe 256, if not 4,095. But you have to keep in mind when you talk about quantization into a fixed number of codes, like 256 codes, has that nonlinear transform already been imposed before you quantize? And whenever you see a quantization diagram like this, it's assuming that the signal is already coming in perceptual space, at least the usual ways that these diagrams are used. So my Chinese fortune cookie on this issue, I was actually given this fortune cookie one night over dinner. 2 small jumps are sometimes better than 1 big leap. And my idea here is if you go 1 big leap, that may show up a quantization step that shows up as contouring or banding, where 2 small jumps are sometimes better. And that would be quantizing at about the J and D level. Now, to bring us back into the big high-level context diagram, I just want to remind you of something that I kind of glossed over. I think it was in class 1, which is basically that digital cinema standards, as far as encoding and decoding and presentation are concerned, are based on a document called DCI, loosely called DCI-P3. That refers to a colored gamut, which is fairly wide, covers almost all of the gamut of traditional photochemical film. But for our purposes today, what's important is the gamma of the display, in other words, the exponent of the power function, mathematically, is 2.6. For HD, the expectation is you'll come out in 709 gamut, which is a little bit smaller than P3 gamut, but standard for HD, and standardized just in 2011, gamma, or the exponent of the power function, 2.4. And that assumes that we're coming out into a display environment of about 100 candelas per meter squared. Your monitor calibration experts locally will know about that. But in CE space, and also even in desktop computer space, we typically use displays that are much brighter than 100 candelas per meter squared, typically 300, 320. And in that case, it's more satisfactory to use a power function on the way out, or if you like, gamma on the way out, of about 2.2. And that number is called for in the sRGB standard that we're all used to at that computing level. And in consumer electronics, well, there's no real standard for that in consumer electronics, but 2.2 would be a very typical number for a consumer TV in a consumer class viewing environment. So not nearly as dark as an HD mastering suite, and certainly not as dark as a cinema. So basically the gamma situation is 2.2 for consumers and commodity computing, 2.4 for HD mastering, and 2.6 for cinema. Now, it was a great mystery to me 6, 7, 8, 9 years ago how you could come up with these different gamma values for different viewing conditions, and what's the science behind that. And basically what I found when I researched that issue is there wasn't a lot of science. So I basically enrolled myself in a PhD program to do some research behind that and also come up with some scholarly papers describing the theory, and also then, we hope, file a dissertation and get a PhD degree. After all, I'm teaching at FX PhD, so that only stands to reason. So one of the research products, if you want to call it that, from my PhD efforts is this journal paper, which was just published. I think it gets a date of February 2014, called Perceptual Uniformity in Digital Image Representation and Display. And so it's a 10-pager. I'll just walk through the pages. It gives you the theoretical background behind what I've just explained to you in what I hope are fairly approachable terms. And there's an important, I think it's important diagram here, which is this one, which is basically, and I'm kind of astonished that nobody published this diagram before I did. Apparently, nobody published this before I did. So this graph has got a certain amount of mathematics underneath it, but it ends up simply portraying the pixel value scale that would be typical of HD or even desktop computing, or even digital cinema with different gamma values, 2.2, 2.4, 2.6, and relating that to the color science behind CIE L-star, which I've already hinted several times in the course, is your reference to lightness, that special word, as defined by the CIE, the governing body for color science standards. So we've got CIE lightness on the scale 0 to 100 on the y-axis, and pixel value scale normalized to 0 to 1 with different gamma values, 2.2, 2.4, 2.6. And to summarize very succinctly for our purposes today, how do they relate? And the answer is amazing. They're almost a straight line. Now, coming from Canada, I call this a hockey stick shape, although I'm not really a sports fan. But there is a little hockey stick hook at the bottom of these curves. But they're all remarkably linear in the majority of the range. What this means is that R, G, and B put primes on them to indicate their perceptual nature. They're remarkably close to L star, in the sense that you could really call them R star, G star, B star. It's the same math. So what that means is visual pixel values as ordinarily practiced desktop computing, HD, digital cinema are remarkably perceptually uniform. And it sort of surprises me that nobody nailed that on a 10-page journal paper before I did, but that's the story. And it's not there right now today, but soon, maybe by the time you see this class, I'll have a preprint version of that paper available to you on my website if you want to go dig into the technical details. So the key point is typically in the middle of the chain, we manipulate those values in their gamma-corrected form, or I would prefer to say perceptually uniform manner. And even in Photoshop, that's what you do out of the box by default. Now, for really high-end work in VFX and CGI, it's useful to manipulate numbers as the photon count, the optical power, the scene-referred light values, whatever you want to call them. They go by different names. And that's completely reasonable, but what you then have to do is push this perceptual transform to the very back end of the chain, because when you launch out into the distribution channel, you need to be perceptually coded. Now, between reference black and reference white, I've been calling those 0 and 1 because that's what makes sense conceptually. That's what makes sense mathematically. But assuming we've come into the perceptual domain, you've figured out that what we loosely call 18% in fact resides about halfway up that scale because it's halfway perceptually. It's called mid-gray, even though physically linear light terms it's 18%. So the rest of this diagram, and I apologize for the fact that it's complex, relates to the different integer coding schemes that are used to convey those numbers between reference black and reference white, but now in integers with a certain number of bits. 8 bits, 10 bits, 12 bits are quite typical. Now, one way to convey those numbers is just numbers between 0 and 255, and let's call those the computer or IT numbers. You could also annotate that sRGB. And I like putting primes on the RGB to make sure that nobody confuses them with being linear light RGB, which are the values that lie in front of the camera. Now, that's a perfectly practical system, and it's used all over the place, like in 1 billion personal computers and on the desks of 50 or 80,000 VFX and CGI artists. But for studio video, the situation is a little different, because in the early days of studio video, 3 or 4 different reasons were identified that made sense to have some footroom region and some headroom region, footroom below reference black and headroom above reference white. Now, one of the reasons 25 years ago was that digital video was basically retrofitted onto huge analog video infrastructures, and analog video drifted around. So one of the reasons for headroom and footroom is just accommodate the drift. Well, we no longer need to do that. But there still remain 3 good reasons to have headroom and footroom and 1 new reason to have footroom. And it still remains completely viable and practical, and some people would argue even necessary to have those regions. And those regions were standardized. Now, they were standardized in 8-bit space in the early days, so reference black was placed at 16 and reference white was placed at 235. And in the consumer domain, 8-bit digital video is commonplace. MPEG, H.264, DVD, Blu-ray, and so on. So these are the numbers that are applicable. And across an HDMI interface, you basically have 2 choices. You can use either one of those coding systems. And there's a mechanism for the HDMI channel to signal to the receiver which one it's using, and also to query the downstream receiver on which variations are available. HDMI also queries the receiver on what pixel counts are available, the number of rows and number of columns. And ordinarily, it's the case that if a source of a signal queries a consumer level receiver and finds that it's using a standard HD format, it'll ship out the 16 to 235. But if it finds that it's a sort of IT-based 1280 by 1024, say, which is not a video standard, then the source will code up the 0 to 255 range. So loosely speaking, this is called IT, or PC, range, and this is called CE range. But really, it stems from studio video. Now, in studio video, the last 20 years, we used 10 bits instead of 8 bits, simply multiplied those 2 numbers by 4. So you get 64 and 940 as the reference levels for black and white. Now, I hate how a non-zero number is used to represent black. And so my term for this number, this is the interface offset plus 16, or in the case of 10-bit interface, plus 64. And our preference for processing is just subtract that. But there's a whole complicated story behind that, and that story is detailed in the book. Now, we will be headed towards YCBCR space, which is the standard space for representing studio digital video with a luma component and 2 chroma components. Those 2 chroma components end up being bipolar above and below 0. Some people will say that they're centered on 128, but I consider that 128 to be the interface offset. The first thing that I do as a mathematician, signal processing guy, subtract it out. So I prefer to think of chroma 0 being the grayscale, and then the chroma components in 8-bit space range plus minus 112. That's a detail of YCBCR space. And, I'm sorry that this chart is so complicated. It's just the way things ended up. We really started from 2 different industries, the video industry, the computer industry, and by now they're all mishmashed and the same. So we're having to deal with these different coding systems, different levels, different reference black, reference white numbers. That's why we just have to live with it. Now, I'll wrap today's class with, unfortunately, a little bit of additional complexity, but I want you to be equipped to get your hands on this and work through it if you're faced with problems in this dimension. Here I'm showing you this very simple equation, y equals mx plus b, and I've chosen M to be 0.95, and I've chosen B to be 0.05. So all I've done is reduced the gain a little bit and introduced a little offset of plus 0.05, 5%. Now, in the video signal processing domain and also in desktop graphics, this equation is used to map an image signal set of pixel values, RGB pixel values, into an output set of RGB pixel values, but they don't use the letters M and B. They don't use mathematical symbols. Instead, they call them brightness and contrast. And boy, is this confusing, because the words brightness and contrast used to describe these two sliders in some old version of Photoshop do not correspond to the common use of our language, the words brightness and contrast. Now, brightness is just the little b of y equals mx plus b, and contrast is just the m of y equals mx plus b. But the brightness and contrast values in these numeric input fields are scaled according to Photoshop numbers. So Photoshop is presenting this processing block with numbers in the range 0 to 255, reference black to reference white, and the numbers you get to pick here are plus minus 100. So the brightness control is equivalent to a B running basically plus minus 0.4. And the contrast number, well, it's wacky, and you have to go and buy a copy of my book and read through that chapter if you want to know exactly how those values relate. Now, the Photoshop dialog box, which I'm showing you here, at least I was able to work my head around what those things were actually doing. And when you adjust the brightness knob, what you're doing is you're taking the image information and moving it up and down the scale. And you run the risk that you might move it below the 0 and have it clip. And if you run brightness in the other direction, you'll just lift the whole image information on top of gray. You'll have really bad contrast ratio in the results. So from that point of view, it's misleading to call that a brightness control, because one of the dominant effects is it affects visual contrast. And worse than that, the contrast control is basically leaving black pegged where it's supposed to be pegged and making the image occupy more or less of the output scale. So you can have a full image input coming in, and you reduce the contrast to make it less bright. Well, that's, in common language, adjusting the image brightness, but that's done with the contrast control. So those things are extremely confusing, and what's worse is that other applications, such as this Mac application, which honestly I don't even remember what application it is, it's got brightness and contrast controls, but who knows what they do. So I want to leave you with the idea that brightness and contrast controls, even if they've got those names, don't necessarily control what you intuitively think of as visual brightness and visual contrast. And also, with Photoshop, we're fairly sure what lurks behind those knobs, but with other applications, all bets off. These things are not standardized. So when we come back to the beginning of class 4, I'll give you a little bit more about contrast, what it means visually and what it means to an instrument. And then we'll launch into some other topics about what happens with RGB on the display side.